Okay, here we are. We're back in section 5.5, and this is example 3. So we have a steel shaft. It's made from two segments. AC has a diameter of 0.5 inches. CB has a diameter of 1. If the shaft is fixed at its ends A and B and subjected to a torque, determine the maximum shear stress. So, I mean, I can look at it and see that it's going to be fixed at the walls. So we're going to have a reaction at B and a reaction at A. And if we have a reaction at B and a reaction at A, then we're going to have holding it in place while it twists. So the compatibility we're going to use this time is that the rotation from B to D has to equal the rotation from A to D. But then at the end of this, I'll also set it up looking at force method. So we always start with equilibrium. Equilibrium. I'm going to draw my shaft here, and I have 500 pound-feet, which I kind of want to get rid of those feet. Let's call it 6,000 pound-inches because I just multiplied by 12, or we could call it 6 kip inches, but I want to go with one of those because of the units of pounds and inches or kips and inches because we're in KSI, PSI, so we'll probably be using the 6 kip inches. I'm just going to assume that right-hand rule, the TB, we have a torque at the wall B, and it doesn't matter which way we assume these, so we're just going to do something crazy here to show you it doesn't matter, it all works out. So here's my assumption in terms of wall forces, and if I sum my torques, and let's just assume that way is positive, then I'm going to have a TA minus 6 kip inches minus TB equals 0. So TA minus TB equals 6 kip inches. Okay, so that's too many unknowns. I need to look at deformation. So we're going to look at the compatibility of deformations. So I know that the rotation from B to D has to equal the rotation from A to D because they are joined at this gear. And when I'm looking at this, I can see that this rotation is going to come from, if I cut it, this is going to come from the torque at wall B. Okay, when I look over here at phi, I have this torque at A, but I'm going to have to look at the rotation. So I have torque of A, but I'm going to have to look at the rotation from A to C and the rotation from C to D because they have different values of J. Okay, because they have different diameters. So, but the compatibilities at this point, the rotations have to be the same. So let's go ahead and get those, our deformation equations set up. So let's start over here at B. So I assumed B to be coming towards me. I'm going to put the butt of my hand right here, like that. See the butt of my hand? So going to the back is positive. So this is the torque from B to D. And now if I sum my torques, coming towards me is positive, I get negative TB, BD, BD, plus TB equals 0. So the torque in segment DB happens to equal the torque at the wall. And now we're going to come over here at A and come backwards. So at A, I've assumed it going into the paper. There's my torque at A. Internal, I'm going to assume positive. So that's my torque from A to C. And I can see that they're equal and opposite. So torque AC equals the torque at the wall. Okay, now I need to come through and I have the torque at A. And I'm coming through here between C and D. So now we're cutting internal here, and I'm going to have the torque from C to D. And there's no other applied torques here, so it's continuing that same torque, but I have to cut it 2 places because of my geometry. So again, the torque from C to D equals the torque at A. So now we can go back to our compatibility and our deformation, and we can combine them. And if I know that phi of BD equals phi of AD, but really what we need to call that is, because I'm using proper signs here, is that phi of BD plus phi of AD equals 0. And the reason is because as this is twisting towards me like this, then from this end I'm having to resist backwards, which is positive. From this end I'm also resisting backwards, but that's negative by sign convention. So this is a positive twist and this is a negative twist according to a right-hand rule. So really it's this twist plus this twist equals 0. So what is my twist from B to D? It's going to be the torque from B to D, 12 inches, that's my length. J is pi over 2, 1/2 to the 4th, and I'm just going to leave the G off because it's all the same material, so it's going to come out anyways. Plus, okay, A to D, I need to come here, torque of A times 5 inches, divided by pi over 2, and then we have 1/4 to the 4th, plus torque of A times 8 inches divided by pi over 2, and we're back to that 1/2, and that's why we've had to cut it, and that equals 0. So I now need to do my system of equations. So my first equation that I have is that TA minus TB equals 6 kip inches. My second equation that I have is, well, let's just simplify and get rid of all these because we can multiply that by that and it comes to 0, is that I have 0 equals 12 TBD divided by 1/2 to the 4th plus 5. And what is TBD? It's actually the force at that wall. Remember, it's our reaction. We're trying to get it down to reactions. So it's the torque at the wall, 5 TA over 1/4 to the 4th plus 8 TA over 1/2 to the 4th. So I have this equation and this equation. So I'm going to go ahead and solve that. Well, we don't want to, let's get it in terms of B in terms of A so that we don't have to substitute twice. So we're going to have that TB equals TA minus 6. So we have 0 equals 12 times TA minus 6 over 1/2 to the 4th plus 5 times TA over 1/4 to the 4th plus 8 times TA over 1/2 to the 4th. And now we need to reduce this equation. So I have 12 TA over 1/2 to the 4th minus 12, 24, 36, 48, 60, 72. 72 over 1/2 to the 4th plus 5 TA over 1/4 to the 4th plus 8 TA over 1/2 to the 4th. So I'm going to simplify and bring this over. So I have 72 enter, 0.5 to the 4th divided by, and I get 1152. And it's working out to be positive, which is perfect because I assumed TA going backwards, and it seems to have to go backwards if this is coming forward. So if I get a positive TA, it means I assumed it correctly. Okay. Equals, and then I've got 12.5 to the 4th divided by 5.25 to the 4th divided by 8.5 to the 4th divided by, whoops, drop that, 8.5 to the 4th divided by plus, and I get 1600. I get 1600 TA. Okay. So I have 1152 equals 1600 TA. So TA equals 1152 over 1600 1152, 1600 divided by 1152, 1600 divided by, and I get that the torque a day is 0.72 kip inches, which means then I go back to equilibrium that torque A minus torque B equals 6 kip inches. So torque B equals torque A minus 6 equals 0.72 minus 6. So the torque of B is a negative, which is good because I assumed it the wrong way, right? I assumed it the wrong way. 6 plus, and I get 5.28 kip inches. So I now have the torque at A right there, and I have the torque at B, and it's negative, so that means the assumption of it coming towards me is wrong. So I know now when I'm looking at this, I do have 500 coming towards me. Actually, it's 6 kip inches, but I have both of those are going backwards because I got a positive for TA, which means I assumed it correctly, and then a negative here, which means it's going backwards. So this is 5.28 kip inches, and this is 0.72 kip inches. So now I can go through and I can start calculating the maximum shear stress. So let me get my blank sheet of paper. Let me find my blank sheet of paper to write on the back. Hold on, sorry. Trying to find a blank sheet of paper here. But I'm not doing a very good job of it. Okay, so that's still not a blank sheet of paper. There we go. So now that I'm looking at my system here, I have 500 pound-feet, which is 6 kip inches coming towards me, and I have torque A and torque B going backwards there, so I have 0.72 kip inches, and I have 5.28 kip inches, and I have a little bit of a change right there. So as I'm coming through, and I'm going to be looking at my torques, there's my change. Then my torque diagram in kip inches is going to be, okay, it's going to be, well, if I'm coming this direction, I have 0.72, I'm going to assume positive, and I can see that this torque coming from A to D is indeed the same as 0.72. So we have 0.72, okay? And as I'm going backwards, I have 5.28. And then I put the butt of my hand where I cut it. So going backwards is positive. That is positive. Torque from D to B. So when I sum, I'm going to find that torque D to B equals negative 5.28. And now I can go through and find my shear stress, which is going to be in KSI. And I have to keep in mind that I have a change here. So shear stress from A to C equals 0.72, okay? And then it's 0.25, and then pi over 2, 0.25 to the fourth. When I'm looking at torque from C to D, it's also going to be 0.72, but this time it's a 1/2 inch diameter divided by pi over 2, 0.5 to the fourth. And then my torque, my shear stress from B to D equals negative, okay, because I have that negative 5.28 times 1/2 divided by pi over 2.5 to the fourth. So let's go ahead and calculate those out. 0.72 enter, 0.25 times pi as a number. 2 divided by 0.25 enter to the fourth times divided by, and I get 29.3. We were in kip inches, inches, inches to the fourth, so we are 29.3 KSI. 0.72 enter, 0.5 times, pi as a number, 2 divided by 0.5 enter to the fourth times, and divided by. And I get 3.67 KSI. 5.28 change signs enter, 0.5 times, pi as a number, 2 divided by 0.5 enter, 4 times, divided by. Minus 26.9 KSI. So we can come through here, and I have this giant up here of 29.3, and then I come down to 3.67, and then when I look over here, it is a negative 26.9 KSI. And so there's my shear stress distribution, and I can see then that my maximum is 29.3 KSI, and that's going to be in segment AC.